friends, in this new video we will discuss about complex number and few basic properties of complex number. Friends, we all know natural numbers, integers, rational numbers and real number. There is another system of complex numbers, there is another number system, that is a complex number. It consists of two parts, real parts as well as imaginary parts. We generally denote this number as z equal to x plus iy. We write this z equal to, here I am going to write z equal to, let me write this, z equal to x plus iy. Here x is a real, x and y both are the real numbers, but with this y we can see that there is another number, that is I and I is a representation of imaginary part. Therefore, this complex number consists of two parts. This is a real part, both are real number, but this is a real part of this complex number, and due to this I, this is an imaginary part of this complex number. When we represent in a coordinate system, we have a plane, complex plane, this is called as a complex plane. We denote this complex number in complex plane, since it consists of two parts, real part that is on x axis and imaginary parts on y axis. You can see that the real number on this x axis are the real numbers or a real part of this complex number, and we know that if the number is on x axis, we can write it as a x comma 0. So, the real part of this complex number, if we write this as a real part of z, that is x, and we write this in order pair as x comma 0, and this is a imaginary axis, this is real axis. It complex plane consists of two parts, real axis and imaginary axis. This is an imaginary axis, and we know y axis, this is a number, this is represented by 0 comma y. So, imaginary parts is denoted by 0 comma y, imaginary z, that is y, and for this we write it as a 0 comma y. So, any number z in this plane is written in terms of x comma y. This is an order pair, x is a real part and y is an imaginary part of this complex number. Now, let us define addition and multiplication for two complex numbers. If I have a complex number z1 having real parts as a x1 and imaginary parts y1, x1 and y1 are both real numbers, and another number, suppose z2, let us denote it by x2 comma y2. Then friends, here you can see that we write this z1 plus z2 equal to x1 comma y1 plus x2 comma y2. This is equal to, this is an addition is an component wise, x1 plus x2 comma y1 plus y2, again real part and imaginary part. So, z1 plus z2, addition of two complex number is again a complex number. So, we get a complex number. Now, we define a multiplication of complex number. If we write this complex number as a z equal to x1 plus I into y1, then z1, this is my z1, z2 equal to x2 plus I into y2. So, if we multiply this z1 into z2, let us multiply directly, so that we can write the formula for order pair z1 into z2 in terms of order pair x1 plus I into y1 into x2 plus I into y2. you can see that x1 into x2, x1 into x2 plus I into y1 into y2 plus I into y1 into x2 plus I square into y1 into y2. Here I is a number used to denote the imaginary part, imaginary number, and value of this I is equal to under root of 1. It is known to all of us, or I square, then we get I square is equal to minus 1. Easily we can see that here. So, I square equal to minus 1 in here we write minus 1, and this will becomes x1 x2 minus y1 y2 plus we can take I common from these two, I into y1 y2 here x1 into x1, this is an x1, x1 into y2, this is my x1, x1 into y2 plus y1 into x2. So, again we get a complex number, this is a real part and this is a imaginary part, and therefore, we get here z1 into z2 equal to x1 x2 minus y1 y2 comma x1 into y2 plus y1 into x2. So, in terms of order pair we get a z1 into z2 equal to x1 x2 minus y1 y2 x1 y2 plus y1 into x2. This is a multiplication of two complex number, addition of two complex number. Let us see some basic properties of complex number. We can see that here complex number, now we denote this complex number up to by order pair x comma y. Now onwards we are using this order pair to denote complex number. So, suppose whenever I have z1 equal to complex number x1 comma y1 and z2 equal to complex number x2 comma y2, just we have defined z1 into z2 equal to x1 x2 minus y1 y2 comma x1 y2 plus y1 into x2. Now, we also seen that z1 plus z2 equal to, we have this complex number x1 plus x2 comma y1 plus y2. Again we know that real number x1 and x2 are real number, and for real number we can write this as a x2 plus x1. This is same, since 3 plus 4 equal to 4 plus 3, this is known to us. Therefore, for this x1 plus x2 we write x2 plus x1, and for this number also we can write y2 plus y1. Okay, what is this? This is nothing but x2 comma y2 plus x1 comma y1. Okay, this is equal to z2 plus z1, z1 plus z2 equal to z2 plus z1. So, this shows that the addition is an commutative property. This is also happens with z2 into z1. This is z1 into z2. If we write z2 into z1, z2 into z1, again we get x2 x1 minus y2 y1 comma, here instead of x1 here we write it as a x2 x2 into y1 plus x1 into y2. Okay, and you can see that this is a commutative. So, x1 x2 minus y1 y2 comma x1 y2 plus x2 y1. Okay, so this is nothing but z1 into z2. That means multiplication in complex number is also commutative. Now, let us define identity element for this complex number. We know that 0 is an identity element for real number. additive identity 3 plus 0 is equal to 0. So, similarly, if we write an order pair 0 comma 0, we can see that x comma y plus 0 comma 0 equal to x plus 0 comma y plus 0 equal to x comma y. So, this 0 comma 0 is an additive identity for this complex number. Now, if we have another number x comma y plus u comma v equal to suppose a 0 comma 0, then we can see that x plus u comma y plus v equal to 0 comma 0. And friend, you can see that we get two expressions, x plus u equal to 0, that means we get x equal to minus x, y plus v equal to 0, that means we get v equal to minus y. So, whenever my number is a u comma v, when I am adding this u comma v to x plus y, and whenever I get this 0 comma 0, the value of u is minus x and value of v equal to minus y, that means minus x comma minus y or minus x comma y, this is an additive inverse of the complex number x comma y. That means if my number is x comma y, then minus z is an additive inverse of this number, which is minus x comma minus y. So, I have additive identity for this complex number, I have additive inverse of this complex number. Now, let us find the multiplicative inverse of the complex number. That is, I am interested in finding z into z inverse is equal to 1. So, we know that whenever I have two number x1 z1 into z2, then their product is x1 x2 minus y1 y2 comma x1 y2 plus x2 y1. This is my multiplication. Now, let us denote this z by x comma y, and this z inverse is equal to suppose u comma v. Then z into z inverse equal to x comma y into u comma v. Now, apply this definition, x1 into x2, that means x into u minus y into v comma x1 is a x, y2 is a v, plus x2 is a y, and y1 is a u. So, this is equal to 1, and for this 1 is a real number, and for this one we can write 1 comma 0. So, from this we get two equations, x into u minus y into v equal to 1. Let us call this as equation number 1, and second one is xv plus yu is equal to 0, equation number 2. Okay. So, from this equation from equation 2 we can see that yu equal to minus x into v and u equal to minus x into v divided by y. So, let us put this value in equation number 1, x into minus x into v divided by y minus y into v equal to 1. Okay. So, we get here x into x square minus x square divided by y minus y, let us take v common, v equal to 1. Again we can take minus 1 common, and let us take reciprocal of this cross multiplication of this. So, minus v into x square plus y square divided by y equal to 1. Now we get v equal to minus y divided by x square plus y square. This is my v. Okay. So let us put here u equal to, therefore come again, minus x divided by y into minus y divided by x square plus y square. Y get cancelled, minus minus become plus. So x divided by x square plus y square. So friend, you can see that I have z inverse in terms of x and y. Now z inverse is equal to u. What is u? X divided by x square plus y square comma minus y divided by x square plus y square. So here I have a multiplicative inverse. Whenever my number, complex number z is of the type x comma y, then I am getting the z inverse as x divided by x square plus y square comma minus y divided by x square plus y square. This is an inverse of a complex number x comma y. X comma y is any complex number. Now friend, just we have seen that the complex number z equal to x plus I into y, and you are thinking about how we represent the number I in terms of order pair. So let us find the value of the complex number, imaginary number I in terms of order pair. You can see that. Okay, so this is my inverse, complex inverse. Now I have, what is a z? Z is equal to, let me write, this is a z equal to a number x comma y. Then we know that we can write this as a x comma 0 plus 0 comma y. This is equal to, now if we take x comma 0 plus 0 comma 1 into 0 comma y. Okay. So you can see that this 0 comma 1 into 0 comma y equal to, so let us see here, x1 into x2, x1 into x2, this is equal to, again you can see that this multiplication 0 comma 1, so this is nothing but 0 comma y, multiplication order pair. Okay. So this is an order pair multiplication. Now let us compare this with x plus iy, right. So this is my x I have taken, this is x I have taken as a x comma 0, and you can see that this I is equal to 0 comma 1. Now let us see I square is equal to 0 comma 1 into 0 comma 1. This is equal to, now let us multiply using this number. You can see that 0 into 0, x1 into x2, that is 0, minus 1 into 1, here minus 1, comma here x1 into y2, this is my x1 and this is a y2. So this is a x1 into y2, that is 0, plus x2 is a 1 and y1 is 0, so plus 0. This is equal to minus 1 comma 0. I square equal to minus 1, and we know that I square is equal to what? Minus 1. Minus 1 is a real number, and any real number we can write it as a minus 1 on 0 comma 0. Since they are real number, they can be represented, they are represented on a real axis, and therefore here I will get here minus 1 comma 0. And you can see that this number, imaginary number I, in terms of order pair is given by this quantity 0 comma 1. Okay. Now we have seen additive identity, we have seen additive inverse of this number. Additive inverse, z is the inverse of this minus z, and minus z is minus x comma minus. When we have calculated z inverse, multiplicative inverse, that is x divided by x square plus y square comma minus y divided by x square plus y square. So, let us see the commutative property. Z1 plus Z1 into Z2 equal to Z2 into Z2 plus Z3 equal to Z1 plus Z2 plus Z3. So, this is a very easy one. Therefore, I would like to skip this, and we will see prove the distributive property of complex number. Let us prove this distributive property. For that, we consider three complex numbers. That complex number we denote by Z1, Z2, Z3, and obviously we take the as a x1, y1, x2, y2, and z2, x2, y2, and z3, x3, y3. So, let us z1 x1 equal to x1 comma y1, z2 equal to x2 comma y2, and z3 equal to x3 comma y3. You can see that z1 into z1 plus z2 equal to z2 plus z3 equal to z1 into z2 plus z1 into z3. I am here, we want to prove this. So, let us first write z2 into z3. Z2 plus z3 equal to, it is obvious, x2 plus x3 comma y2 plus y3. Now, let us multiply this by z1. Z1 into z2 plus z3 equal to, okay. So, let us multiply this number by x1 comma y1, okay. So, x1 into x2 plus x3 minus y1 into y2 plus here y3, y2 plus y3 comma x1 into y2 means y2 plus y3 here, plus x2 is x2 plus x3 into y1, okay. So, this is z1 into z2 plus z3. Let us multiply x1 x2 plus x1 x3 minus y1 y2 minus y1 y3 comma x1 y2 plus x1 y3 plus x2 y1 plus x3 y1. This is suppose 1. Now, let us take z1 into z2. Z1 into z2. So, we have already this number x1 x2 minus y1 y2 comma x1 y2 plus x2 y1. Now, z1 into z3 equal to x1 into x3 minus y1 into y3 comma x1 into y3 plus x3 into y1, okay. Now, let us add this z1 into z2 plus z1 into z3 equal to, addition is component wise, x1 x2 minus y1 y2 plus x1 x3 minus y1 y3 comma x1 y2 plus x2 y1 plus x1 y3 plus x3 y1. So, friend, you can check equation number 1 and equation number 2. This is x1 x2, we can see that x1 x2, x1 x3, x1 x3 minus y1 y2 minus y1 y2, y1 y3, y1 y3, x1 x2, x1 x2, x1 x3, x1 y3, x2 y1, x2 y1, x3 y1, x3 y1. So, right side of equation 1 and 2 are same, and using right side we can write it as z1 dot z1 plus z3 equal to z1 into z2 plus z1 into z3. So, this is a distributive law, left distributive law. Similarly, we can prove the right distributive law. So, what is the right distributive law? Z1 plus Z2 into Z3 equal to Z1 into Z3 plus Z2 into Z3. This is right distributive law. Similarly, we can prove this right distributive law. So, these are the few basic properties of complex number. We have defined complex number in terms of order pair, then we have defined addition, then multiplication, then we have calculated the complex properties as a commutative, then we have defined additive identity, additive inverse, then multiplicative inverse is calculated. Again we have taken distributive property. Now let us find Z1 divided by Z2. Let us find Z1 divided by Z2. Suppose my number Z1 equal to x plus iy and Z2 equal to x1 plus iy1 and Z2 equal to x2 plus iy2. Z1 divided by Z2 equal to x1 plus iy1 divided by x2 plus iy2. Okay, so let us multiply this by x2 minus iy2 divided by x2 minus I into y2 equal to. Okay. So, in the numerator we have x1 plus I into y1, x2 minus I into y2, and in the denominator x2 plus iy2 into x2 minus iy2. Okay. So, this is equal to, let us multiply x1 into x2 minus I into x1 into y2 plus I into y1 into x2 minus I square y1 into y2 divided by. So, again in the multiplication, denominator multiplication, x1 x2 into x2 x2 square minus I into x2 y2 plus I into x2 y2 minus I square into y2 square. Okay. So, we can see that here this is x1, I square is minus 1, minus minus become plus, and we get x1 x2 plus y1 y2, okay, plus I into x2 y1 minus x1 y2 divided by I common we have taken, divided by. You can see that this minus plus get cancel, and I square minus 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 plus, and in the numerator we get x square divided by x2 square divided by y2 square, or we write it as x1 x2 plus y1 y2 divided by x2 square plus y2 square plus I into x2 y1 minus x1 y2 divided by x2 square plus y2 square. Okay. So, in terms of order pair, z1 divided by z2 equal to the real part of this number x1 x2 plus y1 y2 divided by x2 square plus y2 square, and imaginary part is x2 y1 minus x1 y2 divided by x2 square plus y2 square. So, this is the z1 divided by z2. So, friend, here we stop and few next properties we see in the next video. Thank you for watching.